All right, let's talk about something huge that's happening right under our noses. A massive upgrade to the entire internet. It's the big shift from an old creaking address system to one that's actually built for the future. So let's start with a number, 4.3 billion. That's it. That's the absolute maximum number of addresses the original Internet Protocol, IPv4, could ever create. And when the internet was first being designed, that seemed like an impossibly large number. Yeah, turns out it wasn't enough. Not even close. I mean, think about it. The internet just completely exploded. All of a sudden, it wasn't just about computers anymore. It was our phones, our watches, our cars, even our refrigerators needed to get online. And that scarcity, it wasn't just some abstract technical problem for network engineers. Nope. It created a very real and very expensive digital real estate crisis. Okay, so let's dig into this a little. IPv4. This is the OG, the system that gave pretty much every device its first address on the internet. You've definitely seen these numbers before, in that familiar dotted decimal format. But the key thing to remember is that its 32-bit design meant it had a hard mathematical limit. And this is when it all came to a head. This timeline shows you the exact moment the free ride was officially over. IANA, the top-level global authority, was out of new addresses all the way back in 2011. From there, region by region, the wells just ran dry. The free pool of IPv4 addresses, gone, which forced anyone who needed a new address onto a secondary market. And let me tell you, that market is wild. The scarcity is so bad that today, a single IPv4 address can cost you about $50. Now, imagine you're a big company that needs thousands of them. Yeah, you're talking millions of dollars. It literally turned a technical resource into a traded commodity. So what did we do? Well, engineers are pretty clever. They came up with this workaround, a kind of, well, a Band-Aid really. It's called Network Address Translation, or NAT. The idea was to let a whole network of devices, like everything in your house, hide behind one single public IP address. But like any Band-Aid, it came with some serious trade-offs. And here's one of the biggest misconceptions about NAT, and you'll hear network engineers say this all the time. People think it provides security. The truth is, it is not a firewall. It only provides a bit of obscurity, and relying on it for real security is a really dangerous myth. And this slide really breaks down that gap between what we think NAT does and what it actually does. We see it as a simple security shield, right? But in reality, it just adds complexity, slows things down, and it breaks one of the internet's core principles, that direct end-to-end connection. You ever wonder why online gaming or peer-to-peer apps can be so flaky sometimes? A lot of the time, NAT is the culprit. So, faced with these massive limits and a Band-Aid that was starting to peel off, the internet's architects designed a true successor, something built from the ground up for a future with trillions and trillions of connected devices. And the crucial point here is just the sheer scale. We're going from 4.3 billion addresses to 340 undecillion. That's a 340 with 36 zeros after it. It's a number so vast you can't even wrap your head around it. It means we could give every single device on Earth, and probably in the whole solar system, its own unique public address. The scarcity problem is just solved forever. And wow, you can really see the difference visually right here. An IPv6 address is so much longer, and it uses hexadecimal characters. That means numbers 0 through 9 times, and letters A through F. I get it. At first glance, it can look pretty intimidating. But thankfully, they built in some simple rules to shorten them. You can drop the leading zeros in any of the blocks, and even better, you can use a double colon to replace one big long string of zeros. It makes them way more manageable to look at. But this upgrade isn't just about having more addresses. IPv6 fundamentally improves how the internet works. It brings back that end-to-end connectivity that NAT broke. Its design makes routing more efficient for the big backbone routers of the internet. And it was designed with security built in from the start, not bolted on later. It's just tailor-made for things like the Internet of Things and 5G. Okay, so if IPv6 is so much better, what's the holdup? Why hasn't the entire world just switched over already? Well, the answer lies in the migration challenge. The simple and kind of challenging answer is that IPv4 and IPv6 just aren't directly compatible. Think of them as two completely different languages. A device that only speaks IPv6 can't talk to a device that only speaks IPv4 without some help. And that means networks need these transition strategies. The two most common are dual stack, where a device is basically bilingual and can speak both protocols, and tunneling, which is kind of like putting an IPv6 message inside an IPv4 envelope to get it across an older part of the network. So all of this leads to the internet that we're actually using every single day, a dual stacked reality. The transition is happening, even if you don't see it. Today, nearly half of all the users connecting to major sites like Google are already using IPv6. Mobile networks especially have been huge drivers of this adoption, along with entire countries in Europe and Asia that are really pushing it forward. And what this all means is that for the foreseeable future, we're living in a world where both protocols have to coexist. Your phone, your home router, your internet provider, they're all running in a dual stack mode, ready to speak whichever language is needed to get you connected. And that leaves us with a final thought. The Great Migration is well underway, and the future is clearly IPv6. But with so much of our legacy tech built on IPv4, will the original internet protocol ever actually be retired? Or are we going to be living in a two-protocol world, forever?